Welcome back friends to another lecture on quantum field theory and quantum entanglement. So, we have been looking at the Dirac equation and looking at the spin half fields, and we are studying the Dirac equation solutions essentially yesterday. Okay, just to recap, let me show you what we did in the last class. So, we wrote we introduced the Lorentz group, and when we said essentially that we started with the Lorentz group, and the Lorentz group is made up of actually six generators. 3 of them are boost and 3 of them are rotations. These are the generators of the boost, because we have my notation is T x y z, so it essentially gives me x z y t, x t, y t and z t, and then there are the rotations of within x y, y z and z x, and this is given in a generic form because you can write it. You can start with infinitesimal rotations, and then it gives you this nice little formula for the rotation group. Essentially these 6 rotations have satisfy the 6 generators satisfy this very important algebra, which is called the Lorentz-Lie algebra. Okay, and every Lorentz transformation can be expressed in this particular fashion. Now the next step is, are there any similar kind of algebras, or are there any generators which exactly mimic the Lorentz-Lie algebra but belong to a different vector space essentially. So those vector spaces will form representations of the Lorentz group. That is the basic idea. That so this is the exponential, this is called a Lie algebra. This Lie algebra is a group theoretical factor. So a group theoretical way of understanding Lorentz transformations. So now you see that then there is an equivalent algebra. Okay. So before going that, you see that this algebra is essentially a commutator between any 2 Lorentz generators. Okay, there are total 6 generators: 0 1, 0 2, 0 3, 1 2, 1 3, 2 3, 1 2 and 1 3. Okay, there are any of these things, and then you can re-express them in this particular fashion. And these m's are antisymmetric. You remember that m's are antisymmetric, the diagonal elements are 0, and they are symmetric. Okay, they are the 0 1s are symmetric, the 1 2s are antisymmetric. Okay, so with this you can this is the algebra which they satisfy, and the eta is nothing but your standard metric tensor. Metric tensor, this is just eta mu nu essentially, which is the special theory of relativity metric tensor, which is given by your choice essentially, is typically given by you have choice in this. So, but let us take this particular choice essentially, which is also sometimes called the Bjorken-Drell metric, the okay, or nowadays Peskin also uses this. And okay, good. So now the question is, we want to have, are there any completely different algebras which satisfy exactly the same kind of, meaning it's exactly same kind of commutation relation essentially. So this algebra is set, the Lorentz algebra is set by this commutation relation. Similarly, there is one more algebra which we got introduced when we are studying the Dirac equation, but let us assume that I do not know anything about the Dirac equation for the present. Essentially the way we proceeded yesterday is that we have something called the Clifford algebra. The Clifford algebra contains gamma matrices, which is made up of given by this particular representation. So, gamma 0 is equal to 0 1 1 0 and gamma I is given in terms of the Pauli matrices, 2 by 2 Pauli matrices. So, it is a 4 dimensional, this is 2 by 2, okay, this is 2 by 2, it is also 4 dimensional. So, these gamma matrices satisfy not commutation relations, but anti-commutation relations. But the fun part is you can construct a commutator of the gamma matrices in this particular fashion. This S sigma rho sigma, which is the commutator of the gamma matrices, not the anti-commutator. The anti-commutator just gives you the eta mu nu essentially, which essentially sets the setting up of the Dirac equation. And this anti-commutators we can keep it aside, but if you look into the commutator of the gamma matrices, it is 1 by 4 gamma rho gamma sigma. So, this is a commutator and this is given in this particular fashion in terms of the metric tensor and the gamma matrices. The fun part is this commutator of the gamma matrices satisfies the Lorentz-Lie algebra. That means, if you take the commutators of 2 such commutators of Lorentz algebra, because rho can go from 0 to 1, 0, 1, 2, 3, 4, 1, 2, 3 and sigma also can go from 0, 1, 2, 3. Now, imagine that so how many commutators you can construct? You can construct 0, 1, 0, 2, 0, 3, 1, 2 independent commutators. You can think of about them are 6 essentially, and then you can now these 6 generators, these 6 commutators satisfy the Lorentz algebra exactly the same way as the space-time rotations and boosts do, essentially the generators of the space-time boost and rotations do. But remember, the Clifford algebra is in a different space. So, they are in a different space. This is in the Spinor space, spinorial space essentially, but the spinorial space, the S mu nu form a representation of the Dirac of the Lorentz algebra in the spinorial space. That is a basic point essentially that. So, you can think of spinors are also forming representations of the Lorentz algebra, okay, and so they can also be listed as particles. Maybe in the course which we have done in quantum field theory the quantum relativistic theory course, we have started with the Poincare group and did all the representations of the Poincare group, and we said that in the modern version of the quantum field theory all the particles arise from representations of the Poincare group. So, this is an example, but we are looking at Lorentz group. Lorentz group plus translations is nothing but the Poincare group essentially, okay. So, the spinors are represent the spin half particles of the Lorentz algebra essentially, the spin representations of the spin half particles of the Lorentz algebra. So, this meaning forms also, okay. So, it tells you that if you have a psi of x which is a spinor, which is in this complex spinor, which this will transform exactly like S of lambda. S of lambda is again gamma mu gamma lambda, a representation of this times psi of lambda inverse of x essentially, so lambda inverse of x. Now, this is the important point, and so we can show that the spinor particles will appear as representations of the Lorentz algebra in this particular fashion, and then we went to studying the Lorentz covariants essentially, what are the possible Lorentz covariants which we can construct from the spinors essentially, okay. So, I will go into this in greater detail and then we finally wrote down the Dirac Lagrangian, but today let me go through it a little bit more in detail. So, what as we have seen the Dirac fermions or the Dirac particles form a representation Okay, to be more accurate, the Clifford algebra. Okay. Forms a representation of the Lorentz algebra so when I mean so Lorentz Lie algebra, okay, the Lie group algebra essentially, which is this given in terms of this given in terms of Mij 0 I Mij, okay, forms a representation of the Lorentz algebra. Okay. So, S of lambda is equal to 1 by 4 some gamma mu commutator gamma sigma. So, that means that if we have a spinor, so spinor Dirac spinor, which is made up of psi 1, psi 2, psi 3 complex numbers. Okay. So, this transforms of S of lambda psi of lambda inverse of x. So, psi prime of x essentially, okay, is equal to S of lambda. So, this is how this psi transforms under okay, under Lorentz transformation. So, this is how the psi transforms a spinor transforms So, now just to make normally what we do, we start with the Dirac equation and then say what does it, how does it transform under the Lorentz transformation. So, but in this class what I have done is the reverse, the complete converse. I say that there are these algebras which form a representation of the Lorentz group and representations of the Lorentz group, and from there I can define something called vector spaces of spinorial vector spaces and how they transform under the Lorentz transformations. Now, what we have to do is we are doing the reverse way essentially. So, we are now saying that how does it meaning how do you form a what is the equation of motion this spinors satisfy under Lorentz transformation, which is invariant under covariant under Lorentz transformations, and that is how we will retrieve the Dirac equation. So, normally we in the previous course of relativistic quantum mechanics, what we did was we wrote down the alpha beta matrices, put consistency conditions on them and then derive the Dirac equation. But in the quantum field theory course we are doing the reverse essentially. We start with the algebras which are the Lorentz Lie algebras, and then we are looking for representations which exactly satisfy the same set of Lie algebra essentially, which is the commutator of the gamma matrices of the and the commutator of the gamma matrix, which is nothing, which form the Clifford algebra. From there we are trying to reconstruct the Lagrangian and so on. So, for this we will see how the psi transformed, and now let us look at what are the products of psi, which how they transform under the Lorentz group essentially. So, under the Lorentz transformation, one of the first things we looked at already the bilinear covariants. Let us just do a little bit more exercises with them, 1 or 2 exercises just to warm ourselves essentially. The first one of the bilinear covariants which we have looked at in the last class was the scalar, and the scalar is nothing but psi bar x psi of x, where psi of bar is gamma 0 psi, okay. So, this is the gamma 0, the gamma 0 matrix appears here essentially, and so this is how you define psi bar essentially. Psi bar is equal to psi dagger gamma 0, and dagger is nothing but psi star whole transpose. Okay. Now the question is, how does it transform? So, psi bar prime of x, psi prime of x, you can show that this is nothing but equivalent to psi dagger. I am not doing the full derivation, inverse of x gamma 0 psi of lambda inverse of x, and this is nothing but your, okay, you can expand this and you will see, okay, there is an s sitting here because there is, oh, okay, I should write down the middle step also just to make sure. So you can put an s because the s is because you use this formula, we use this formula. So you have s of lambda dagger gamma 0 s of lambda psi of lambda inverse of x. So this entire thing, so psi dagger of lambda inverse of x, this is nothing but gamma 0. This is the condition actually when we look at the covariance of the Dirac equation. That is how we derived it in earlier times, but this is nothing but gamma 0. The gamma 0 is invariant under this particular transformation. So, psi of lambda inverse of x. So, because of the if you use the representation of s of lambda, which is nothing but 1 by 4 commutator of gamma mu gamma nu, you will end up with this. This is nothing but. So, psi of x, psi bar of x, psi bar of x into psi of x is nothing but, I do not know why I am putting 2, okay. So, this is invariant under Lorentz transformations and this is called a scalar. So, the main argument essentially is that, okay, is that this is the crucial point, that you have s of lambda dagger gamma in general gamma mu should be equivalent to this entire combination should be equivalent to lambda mu nu gamma nu, essentially that is the basic idea. So, that is what we will see essentially. Now, so this can be clearly seen, I will not do the other examples, but let me do one more example which is important, which is the vector, which is useful for us. So, vector. So, the claim is that psi bar gamma mu psi is a Lorentz vector. So, that means that psi bar of x gamma mu psi of x transforms as lambda mu nu psi bar of x gamma nu psi of x. That is how it should transform, because the vector should always transform as a lambda with respect to the lambda matrix, essentially that is how it should do. So, this is like a vector, it is like j mu or k mu, a mu, any of these things which is, so this is a current, essentially j mu transforms as a Lorentz vector. If it transforms as a Lorentz vector, its form should be like this. In fact, it is obvious that it looks like it should transform essentially, but there is some condition. So, the point is that it turns out that for this to work out, we need a condition that s of lambda inverse gamma mu s of lambda is equal to lambda mu nu. This is the condition I was mentioning, gamma nu. This is also condition required for the covariance of the Dirac equation, which you will remember that which was covered in the relativistic quantum mechanics course, but anyway independent of that course you see that this is the same condition which will appear it. Now this can come, it will come automatically if you have a representation of the, so this you can see now the, okay, now you can see, you can derive this condition, why this condition comes. So you have psi bar prime x prime gamma mu psi of x prime psi is equivalent to, so you would put psi dag, okay. So now you expand everything, now you can show that you will end up with having psi bar, okay, x s of inverse gamma mu s of lambda and then psi of x. So this is obvious to see, this you will get it because just because you need s inverse coming on the because s prime and just using this thing, okay, just using s of lambda is equal to lambda inverse of x, okay, okay, this is lambda inverse of x, lambda of x, okay, this, let me write it more accurately, yeah. So this will end up being this. Now this, now if this goes as this, you have your claim satisfied. If s of lambda inverse gamma mu s of lambda is lambda mu nu gamma nu, then this current transforms like a Lorentz vector, okay. Now okay, I think you are all convinced up to here, okay, this is the same thing what we did essentially, okay. Now just following the same steps essentially. Now the point is, how do you show that this is true? To prove this, okay, to prove this you had to use, to prove this you have to again take the representation of s. Suppose lambda is equal to exponential, that is what we wrote down right in the previous class, omega rho sigma m rho sigma. So which is, if I take the linear term, which is 1 by 2 omega rho sigma m rho sigma plus so on. So now s of, similarly if you take the representation of s of lambda, that will be exponential 1 by 2 omega rho sigma, instead of m you put in s. So it will be the same thing, rho of sigma, because s forms a representation of m, s forms a representation of. So this is 1 plus 1 by 2 omega rho sigma s of rho sigma, okay. You know what is the definition of s, so put it back, okay. You know what is the definition of s, so you put it back and then check for this relation, that is the basic idea. So then you will see this requirement just becomes s rho sigma gamma mu is equal to s rho sigma gamma mu commutator is equal to minus of m rho sigma mu nu gamma nu, okay. So okay, this is, and this we can show that this ends up being m nu rho sigma. Now m rho sigma you can express this as S rho sigma gamma mu is equal to eta mu gamma sigma minus eta sigma mu gamma rho. Okay. This you can show, actually the way you show it is take the commutators within the commutators. So, this will be essentially that you have on the left hand side LHS will be equivalent to 1 by 2 gamma mu gamma sigma. Okay, you have to take, and then this will lead to what is it and everything, and you will end up having this formula essentially. So, that is how you prove this. Now, this once you prove this claim, okay, so this will end up being, how will you show, and this is nothing but this thing, because S inverse, you take S inverse again 1 minus omega rho sigma S rho sigma and then gamma mu, and S lambda you take it again 1 plus half this thing. So, this condition and this condition are the same essentially. So, you end up having 1 plus omega mu sigma S rho sigma times gamma mu times 1 minus, maybe it should put a minus sign here, 1 minus omega rho something else. So, lambda delta S lambda delta, take this, okay, and then this should be equivalent to, at the end of the day this will end up being this condition essentially S rho sigma gamma mu, okay. And once you prove this thing, you are back in business. So, you have the proof that this is proven essentially, this is proven. So, this is hence proved essentially, okay. So, you take the representation of the Lorentz group essentially in terms of the Clifford algebra, put it back, and you show that this will lead to these conditions essentially. These conditions are hence proved because the moment you put in the gamma matrices and everything. So, this will give you this relation to be true, and from there you can show that the vector transforms like an actual Lorentz vector. The vector current made up of 2 Dirac particles, okay. Current made of Dirac particles transforms as a Lorentz vector under Lorentz transformation. So, this is the basic idea. Now, we look at the so then similarly you can show that what transforms, there is another thing which is nothing but your Lorentz tensors. So, which is nothing but psi bar sigma mu nu psi. So, this transforms as a tensor. So, as means that means you have 2. So, psi bar x sigma mu nu psi prime of x prime transforms as some lambda mu nu rho lambda nu delta sigma lambda mu nu lambda rho sigma psi bar of lambda inverse of x sigma rho rho and then psi of lambda inverse of x essentially. So, this is the basic idea that this transforms as a Lorentz tensor, you have 2 lambda matrices. Okay, so that means the two Lorentz transformations essentially. So this means 2 index Lorentz transformations. Because it has 2 indices, one Lorentz transformation for each index. For each index, so this leads to a tensor like current for Dirac particles. So at the end of all this, so what we will end up with, okay, so you have all these bilinear covariants which we have written in the last class, which are, so the finally all the bilinear covariants, let me just list it, like I am ending this lecture just like similarly like the previous way. Psi of x which is scalar. So this is pseudoscalar, then there is a vector, there is an actual vector, so the gamma phi essentially I am introducing, okay, I have to introduce gamma phi, I will just introduce it, and there is a tensor psi bar sigma mu nu psi bar sigma mu nu gamma phi psi. So what is this? So this is scalar, pseudoscalar. This is a vector, actual vector. Tensor. Okay, the gamma phi is defined as I gamma 0, gamma 1, gamma 2, gamma 3. So this is a generator of parity, and it's also something called chirality. Okay, the gamma 0 essentially sets the parity of the current or the bilinear covariant essentially. So if it is axial, that means the parity is so it is a pseudoscalar, so it's not invariant under parity, and axial vector picks up a minus sign under the vector current picks up a minus sign essentially anyway. The axial vector acts opposite, it cancels the minus sign. Similarly the tensor. So the gamma phi is associated with the parity of the bilinear covariant. The bilinear covariant. So these are all these bilinear covariants essentially. Covariants. Okay. Now you haven't got introduced to the gamma phi earlier also, but anyway I just want to repeat it a little bit more. So with this now we will not start looking at the Dirac equation and the Dirac Lagrangian. We will start with the Dirac Lagrangian and then derive the Dirac equation, and then we will go further essentially. Okay, and then finally hopefully we will soon start looking at defining the Dirac field and how to quantize it. Okay, let me stop here. Thank you very much essentially. So I will soon meet you in the next class where we continue working with the Dirac equation. Okay, thank you very much.